Well, welcome to the chapter on acid-base, well, not acid-base, other equilibrium, although we do cover buffers in this one. First of all, I'll talk about ethylene glycol poisoning. This is interesting because the cure for ethylene glycol poisoning is actually to get rip-roaring drunk. So if you find yourself, well, I mean, of course, you're at home and you accidentally, instead of drinking a big glass full of lemonade, you drink a big glass full of antifreeze, you should go to the hospital. But let's say this happens out in the middle of nowhere in the bush in Australia and there's no hospital nearby. Get rip-roaring drunk as soon as you can. Uh, because, well, what can happen is that the ethylene glycol will be oxidized to form glycolic acid, and that will make your blood pH drop, and it causes a condition called acidosis. So what the hospital can do is they can inject you with sodium bicarbonate, baking soda. Don't just go and grab baking soda out of your closet and then inject it into your bloodstream. No, no, no. You got to have ultra pure, and you have to be at the right concentration, because otherwise you can put yourself into alkalosis, which is also bad. But what happens with ethylene glycol poisoning? Your blood pH drops and it diminishes the oxygen carrying capacity of your blood. So here, the oxygenated hemoglobin, hemoglobin, hydrogen, and attached to the oxygen, it can form hemoglobin and then acid. If you increase the acid load, you will shift left by Le Chatelier's principle, and you will not oxygenate your blood. So obviously, blood needs to have a way to regulate pH, and we do, and we have a buffer. Specifically, we use carbonic acid, which is also a byproduct from oxidation. So carbon dioxide plus water makes carbonic acid. So we use our waste carbon dioxide to regulate our pH. That and so bicarbonate, so sodium bicarbonate, baking soda. So it's basically baking soda and soda water is in our blood. That's what keeps us from our pH from jumping and up and going down too much. Also, so buffer protects it from having both alkaline and too acidic. So I've been working, like I've had cuts on my hands and I've gotten bleach. Like if I'm working in the laundry, I get bleach on my hands as a cut. Man, that hurts. I'll get a little bit of bleach in my blood, but I'm not gonna roll over and die because I've got the buffer in my blood system. The pH doesn't go up very much. And likewise, one time I was making mojitos and I was slicing limes and I cut my finger with a knife, and boy, that really hurts, especially when it's coated on with something that has a pH of 2. It really stings, but it just stings. It doesn't do anything else other than that, because of the blood buffer system that I have. So what does a buffer do? A buffer resists the pH change, and it has both a large amount of a weak acid and its conjugate base. So that way the weak acid will neutralize base and the conjugate base will neutralize the acid. And there is an equation on how you make a buffer. You make its acid and its conjugate base together to form a buffer solution that has both the weak acid and the conjugate base. And here is an equation that uses the Henderson-Hasselbalch equation. pH is equal to pKa plus log of the base concentration over the acid concentration. So this is the same as using the equilibrium relationship, but it includes the exasmall approximation. If you don't want to use concentration, you can just use moles of base over moles of acid. You don't have to use concentration each time, because the brackets means moles per liter, so you can get rid of the liters on both sides and just have moles. So if you want to use the equation I've written there underneath in pink, that'll work too. So if you take one thing away from this class, take away Le Chatelier's principle. If you take two things away, take away how to use this equation. It's a very, very useful equation. You use this in many classes, many biology classes as well. So let's do this. Calculate the pH of a buffer solution that's 0.05 molar benzoic acid and 0.150 molar in sodium benzoate. For the Ka for benzoic acid is 6.5 10 to the minus 5. So the pKa, this is minus the log of the Ka, 6.5 times 10 to the minus 5. plus the log of the concentration of the base. Which one is the base? It's the one that's going to have the alkali metal in front of it. It's also the one that's not called acid. Okay, so benzoic acid is the acid. So the base is the one that has the alkali metal, so that's 0.150, and this is 0.050 here. So it's a log of 3. So of course that going there, let me put that in my calculator as soon as I find calculator. Here we go. So minus log of 6.5 times 10 to the minus 5 plus the log of 3. I'll just go ahead and put 0.15 out of 0.05. What the heck? And this is, how many sig figs? 2. This is equal to 4.66. And done. Wasn't that easy? After doing all these equilibriums, and I'm still, I hate the sulfuric acid one where I have to go through and do the quadratic equation. Now it's just straightforward. Just put in an equation, plug and chug. So let's see if we can do this one. 0.25 molar HCN, so that's the acid because it has an H in it, and 0.17 molar potassium cyanide, that's the base, it has the alkali. pKa is that. Tell me what the pH of this is. Okay, so hopefully you should have gotten this, 9.14. Okay, so now I'm going to talk a little bit at length about logistics curves. Logistics just means the log plots. So here is the titration of a strong base and a strong acid. So you start off with strong acid. So initial pH is about 1, so it's about 0.1 molar. And you see over here, so the y-axis is pH, and the x-axis is the amount of sodium hydroxide base you've added. And so this is a strong base and strong acid. So the salt is going to be about pH 7. That's where you see the equivalence point. And the equivalence point is also where the second derivative of the plot equals 0. So if you have any calculus, let me explain. The second derivative being 0 tells us when there's concavity. If you noticed here, this part points up, this part points down, and where it switches from up to down is right here. At this, let me change the color, this spot right here. There's something special about that spot. That's where the second derivative hits 0. That's where the concavity of the function changes. And this is also how computers calculate it. Look for the second derivative where that equals 0. So that will tell us where the equivalency point is, and also since it's a strong acid and a strong base, it will be at pH 7, and this is also where the moles acid equals moles base. So this is the information you can get in the chart. And so after then at that equivalence point, all the acid has been destroyed, and now you're just adding base. It just asymptotically approaches the pH of whatever it is you're dropping in there. Okay, so let's do the opposite, strong base and strong acid. It's the same thing, but this chart is backwards. We start off high, and you still have the concavity change. This concave down, this is concave up, and you have the equivalency point. Equivalency point still at 7, and it's also where the second derivative equals 0, and that's where the moles acid equals moles base. So same idea, but it's just the other way around. So let's look at a weak acid and a strong base. Start off with weak acid. There's a couple things. Notice that there's a sharp increase in the beginning, but then there is a point here. This is where the second derivative equals 0. So because this is concave down and this is concave up, and then look over here with concave down, we have another point there where the second derivative equals 0 right there. Right, so there's two parts here. The other one, so the first one is also this is also the pKa. So that where that second derivative equals 0, that's also the pKa of the acid. So that's one way you can determine it. Also, you notice this range right here. That's the buffer range. So along this range, if you add acid or base, the pH doesn't change that much. So it's a relatively flat range. This is where the buffer is going to be effective. So the buffer is not going to be effective up here. It's only going to be effective there in that range of pHs. And since this is a weak acid and a strong base, the salt with the neutralization of it is going to be above pH 7. So that's up there. And then over here, here's the opposite. Here's a weak base and a strong acid. And you can see here there's still this other equivalency, this part where there's a concavity change. You have the same thing, the half equivalency point. Also well, I guess you could calculate out the pKb there. But then there is a buffer range along here. So you have a buffer range, same thing, and the equivalency point for where the moles acid equals moles base is going to be below pH 7 because it's a weak acid and a strong base, and we talked about that last chapter. If you have a polyprotic acid, you can have two buffer zones. So there's a buffer zone here and a buffer zone here, and you also have the concavity changes in those points, and then you also have the half equivalency point. So you have all these things here, and this looks like so sulfuric acid. This one's pretty close, so it's a little less than 7. So it's much less than 7. It's about 5 for this one, the first equivalency point. So, but you see the two humps there. But you can see there the concavity. You have the concave down, concave up, concave down, concave up, concave down, and you have 4 spots where the second derivative hits 0. And that will give you some important information. So if you look at these graphs, the shape of them, they tell you things. So I'm hoping then you learn about this and look at the graphs and think about what it is they're telling you. So that's part of the way I was taught math and taught to look at functions and looking at what information I can get from that. So hopefully I'm passing some of this knowledge on to you. Even if you haven't had calculus yet, I was taught this without knowing calculus as well. So we will continue next time to talk about other aqueous equilibria other than acids and bases.